Hello everyone, this is the Seep tutorial for University of Guelph student in Inch 3607. We'll start to analyze this earthworm as a geometry with Geo-Studio software. So we'll open the Geo-Studio software and so we have different licenses: full license, basic license, student license, and view license. So we have to click on the student license, which is free. We can download from the software website. We have to click on Key Analysis Add and Seep Analysis Steady State, which is free for a student license and you can use for this example. So these are the defaults for analysis. We just leave it whatever it is, that's fine. You can search for the definition of each one later, but for this example let's just start with save. We can save this with Seep example name. Click on save. Oh yeah, maybe we have to change the name to Seep just without backslash and save. So the first step would be the geometry. For this example, we just want to insert the picture because we don't have enough time. We want to insert the picture and use the picture and change the scale of the picture. So then you have to click. We have the picture here. We have to change the scale of this picture to match with the coordinations in the Geo-Studio. We have point A in 0, 0 and point B in 5 for X and -2 for Y. So we have to scale the picture in here. We have to write 0 for X, 0 for Y for point A, and for point B we have X5 and Y -2. Apply. That's it. We have the picture with the same scale that we need in this software, the Seep. Zoom the objective and then we can start to define the region. So you can see for point A, point B, all of the coordinations are really same as the software coordination. That's fine. We can start with draw regions, lines, or points. Let's do the region. For point by point, we can click on the picture and choose the area, angles. That's it. We have the region. And for point A, 1, 2, 3, and 4. If you go to key in and material, the regions, you can see the points: point 1, point 2, 3, and 4. Yeah, we can see them on the picture, the point numbers. So we have the region. That's it. Close. And let's start the material. We have to define the material. Next step, you have to click on add, change the name to maybe earthworm, and we can change the color too if you like. We will change it to this one, and let's change the material model to saturated and unsaturated, because it can be saturated, the earth type can be saturated or unsaturated or both. So let's define the water content function first. We have two kind of function in this analysis: water content function and hydraulic conductivity function. For water content function, click on this bottom and click on add. We can change the name to clay or something, because as you know, the earth type mostly is clay. So we can change the type to data point function and click on estimate. Yeah, this is the option for the situation that we don't have enough data. So we can, for this example, we can use this. So click on estimate and estimation of the method. We can use the grain size data or sample functions. If we use the grain size data, we have to insert the saturated water content, diameter at 10% passing or 60% passing, and the liquid limit. The data maybe you can find in the laboratory, but for now I'm more comfortable to change it to the sample function. And as you can see, as a default, software has the sample material, like for clay, silty silt, silty sand, sand and gravel. So if we click on the clay, and that's it, we have this material water content function, and you can see the curve of the water content function for the suction, the horizontal axis. The next step is the water content function. We have to click on the clay. It is really important. Most of the students didn't do that, and it may have a problem. So then you have to go to the hydraulic conductivity function. It's somehow same. You can change the type again to data point function. Click on estimate. Change the water content function to the clay that we made it before. Change the hydraulic conductivity in saturation to E-3, which is for clay, and the residual water content. So now we have the hydraulic conductivity function in the curve. As you can see the curve, you can change the name to clay H for hydraulic and C for conductivity. Close. And again we have to click on clay hydraulic conductivity here and close. We define the material, and we just have to allocate this material to the earth dam area. Just click on the area and that's it. We have the geometry, we have the material. The next step and the third step would be the boundary condition. Click on key in boundary conditions. As a default, the software has zero pressure and potential seepage phase. We don't need the zero pressure. We can delete that or not, doesn't matter. We don't need that one. We can click on add and new hydraulic boundary condition. And for upstream, we have the first boundary condition. All of the points under the water level in the left side, it has 8 meter as the total head. We can write 8 meter for the action, and we can change the color. It's the same as the zero pressure. We can change it to green. Click on add new hydraulic boundary condition and change it to change the name to downstream. For the downstream, we just have one point which has the total head equal to 0. So we can change the name, change the number to 0 meter for this point, and in the right side of the earth dam, as you can see, it doesn't have any water level. The water level is 0. We can change the color to yellow, and that's it. We have all of the boundary conditions that we need. We have the potential seepage phase, we have the upstream and downstream. The potential seepage phase belongs to the points that the total flux is 0 for them, and you can see for all of the points in the right side of the earth dam we have this situation. That's it. Now we have to allocate this boundary condition to the earth dam area. So let's start with the upstream. If we click on the left line, you can see it will click on all of the points, but we don't need this boundary for the points on the top of the water level. So we can just remove it, remove this boundary, and we have to separate this line to two lines. The line for the points below the water level, and the line for the points on the top of the water level. So we have to draw the points and draw one point on the water level, and just click on the upstream boundary condition again, click on this line, and as you can see, the lower points all have the same boundary condition. For the right side we have the potential seepage phase, and for the downstream we have just one point, so we have to select the points under the boundary condition. And if we zoom, we can see better that for this point we allocated boundary condition, which make this point yellow. Now we define the geometry, we define the material, we allocated the material, and we defined and allocated the boundary condition. That's it. Just save and click on verify to see if there was any error or not. There was 0 error and 0 warning. That's it. It was successful example, and we do not have any wrong issues here. Close and click to solve, save again and start. Close, and then we can see the post-processor analysis. Yeah, we have the result right now. We have the equipotential lines, we have the water level in the earth dam, we have the seepage of the water in earth dam by black lines, and we can see the potential of the water 7.57, 6.56, 5.5 decreased from 8 to 0 for these potential lines one by one. So that's it. We just analyzed the seepage of the water inside the soil of the earth dam. Thank you for your patience.